Okay, Kirchhoff's rules. Charge can accumulate except at a capacitor plate. Hopefully you've done problems to convince you if you have even a microcoulomb of charge sitting on something, you don't want to be in the same building with it. Okay? Because of the tremendous amount of energy, tremendous amount of repulsion that like charges have for each other. Another way you can accumulate charges at two places capacity. We've talked extensively about that. You really want to understand that. The other is electric fields are conservative. Now, that's not usually the way Kirchhoff's rules are explained, but that's it. But let's see how that applies to circuits. Applied to circuits, the first law says that the change of potential around a loop is zero. Second says total current into a branch point equals the total current out. Now, I've often stated the net current into a branch point is zero. Okay, as currents out are just considered negative currents in. So let's look at an example. We don't need Kirchhoff's laws here. Very simple, parallel. Set of resistors. So we got a source. Got the resistor R1, resistor R2. Now I'm going to ask you, just sketch this, and then show me the different currents, you know, like I1, I2, and so forth, just use arrows with identifying symbols, I1, I2, I3, whatever. And show me what the different currents are. Okay. Well, yeah, think about it. Your current comes out of the, well, your current's going to flow one way or the other. All this current I1. Okay. Up here's a branch point. So current I1 branches off. Its currents I2. And I3. And then you might shout, there we got a current I4 here. Now it's going to turn out that this I4 is the same as I1 for several reasons. One is there's no branch point here, so the current can't split. Okay? So the current can't accumulate between here and here. There's no place for the current to accumulate. There's no capacitor there. Right? So we can say that I4 equals I1. Currents can't accumulate and no branching. Well, keep this thing, I want to talk about this in this note. There's no branching. Between node 1 and node 2. By a node, I mean a place where the current does branch. Current branches here. There are 3 possible paths for the current. Current branches here. There are 3 possible paths for the current, 3 possible currents that come together with these nodes. Okay, so I1, I4 equals I1. So I'm going to leave that label I4 for right now, so we'll make that observation. Okay, and normally you would know that there's no branching between the nodes, so that this, if this is I1, this has to be I1. Okay. Okay. Now, what's the voltage drop around this loop? And I should have made this bigger so I can label loops. But this will be loop 1. And I guess we'll make this meaning this loop and this loop. There are 3 possible loops. Yeah, let's get 3 fingers up there. There are 3 possible loops in this circuit. There's this loop, there's this loop, and of course, there's a loop that's the whole circuit. Okay? What's our principal? Electric field is a conservative. Conservative mean? Means the line interval around the whole thing is 0. But it comes down to you have no potential change. If you go from any point on this loop around the loop and back to that point, the potential is the same as where you started. So you have zero potential change. Okay, same is true for this loop, and the same would be true for this big loop. Okay. Now, what's the total voltage drop across that top loop? Well, you want to first write the expressions for the voltage across two resistors, each of the resistors. Loop. Oh, heck. I don't know. This is recording, so I think we've lost some stuff, but let me go over it. I think I said I4 has to equal I1. Since charge can't accumulate, and there's no branching between node 1 and node 2. I wrote down node 1 here. This is a branching point. That's called a node. Okay. You can come into here and go this way or this way, some combination thereof. There are more than two currents. Shows up 3 more currents. Okay. And same thing here. That's another node. That's node 2. There's no branching between node 2 and node 3. So that the current here has to be the same as the current here. Okay. So we're not going to have two separate currents. If we did, if these currents were actually different, you'd have an accumulation of charge between these nodes. Now, if we have a capacitor, that could happen, but there's no capacitor. Okay, there's no place for charge to accumulate. It's not going to accumulate in the source. So I4 is equal to I1. Made that node. Okay, now I said, okay, let's look at loops. We've got a loop here, which is just this top loop, and then we've got this bottom. I also noted that the whole current, the whole thing, all the way around the periphery could be a loop. But we don't have three independent loops. Okay. In other words, if we did say there's a loop all the way around here, it would just be a combination of this loop and this loop, wouldn't it? Okay. It's like linear independence. This loop is not independent of these two loops. Yeah, I was going to say something. Okay, so now we've got loop 1 and loop 2, and we're going to use the fact that electric field being conservative, potential change around the loop is 0. Means if we start here and move around to this point with the same potential, we started at same potential energy per unit of charge that we started at. So there's no potential change between this point and this point. There's no potential change as we go around the loop. Same with going around this loop. From any point on the loop back to that point, the total voltage change, potential change in voltage would be 0. Okay. So what are the voltage drops in loop 1? Okay, well, one of them is I3 times R1. Just multiply current by resistance. There's a voltage drop from here to here if the current is in this direction. Now, since I don't have numbers on these resistors and so forth, although this simple circuit is pretty obvious what happens, I just make my best guess as to the direction of the current. Okay. Ultimately, in just a minute, we're going to get some simultaneous equations. You're going to solve those simultaneous equations for I1, I2, and stuff. Okay. And if you get a negative, that means you chose the wrong direction. You got a big complicated circuit, you're not going to have any idea what direction some of these things are. You just pick the most convenient direction. Comes out negative, then you reverse it out. Okay. Anyhow, voltage drop from here across here. If the current's in this direction, you have to have higher potential here than you have here. to drive the conventional current on a positive charge in this direction. So your voltage drop is I3R1. Now, what is your voltage drop across resistor 2, where the current is I2 in this direction? Is it I2R2, or is it negative I2R2? Okay, so I got a quick answer to that is correct. You got around the loop in this direction, the current has gone in this direction. Okay, so the loop takes in this direction, the current takes in this direction when you go through that resistor. So it's going to be minus I2R2. And that's all we have in this circle, and that's 0. Well, there's an equation. Assuming that the resistors are known, you now have an equation with 2 unknowns, okay? Now we've got 3 currents once we set I4 equal to I1, okay? How would you write? Voltage drop across loop 2. It is loop 2, isn't it? Yeah. Okay, that's pretty good. Okay, fine. Yeah, okay. Couple little mistakes. Okay, and loop 2, you're going to round this one. Your voltage drop here is 3 volts. Now, there's a little confusion about voltage drop being positive. Well, the voltage does go from, like, say 3 volts to 0 volts, okay? If that happens to be voltages. So that looks like it's a negative change in voltage. Yeah, that's true, but a negative change is a drop. So if you have a change of negative 3 volts, your voltage drop is 3 volts. Does that make sense? Okay. So the voltage drop across R2 and loop 2. Going to be I2, R2. These are going to be simultaneous equations. Notice these are just going to cancel each other out, right? I'm going to line these equations up. This and this are going to be equal and opposite. But of course, one loop would go across the resistor this way, and the other would go across the resistor this way. Okay, well, you have I2, R2, and then you have your voltage drop across the source, which has voltage V. Call that V as voltage of the source. Okay. And well, we're going from negative to positive. Remember, the short one is negative, the positive which pushes the current in the direction of flow of positive charge, even though the charges are actually going this way. Okay. That looks like it has more sign, but what that's on. Okay, you have I2, R2, voltage drop across this, and your voltage drop across this is negative V sub S. And that the voltage drop is 0. All right. Okay. Now, what else can we do? Well, that's pretty much all we can do with the potential change around a loop. Because the only other possible loop we would have would be the whole thing, which is just a combination of these two. And that's not going to help you. It's not going to give you any additional information. If you happen to write it down and you don't have enough equations, you're not going to get a solution. Okay. Maybe you write that one down as well, and then write still another. That could work because you know. Well, you think about what that do to your system. Okay, total current into a branch point equals total current out. How are we going to use that? Can we write an equation? Okay, so we can't use any more loops. We've got to use a branching point, a node. Okay. So which node do you want to use? Well, everybody wanted to use node one. Okay, so we use node one. At node one, you have total current in. I1 is in. Okay. Now I2 is out. So negative I2 is in. Okay. And I3 up here is out. So you have a negative I3 equals 0. Okay. Now we have another equation. Since we put I4 in here, I left it in there. And you might actually accidentally do that in a complicated circuit. So I'm going to leave it in there and then see what the mathematics does to it. So can you solve those four simultaneous equations? Okay, so I've taken these three equations and I've lined up my I1, I2, and I3. And then we've got an I4 equals I1. And these three equations allow me to solve for I1, I2, and I3. Three equations, three unknowns. Okay. And having solved it, then I can just say, well, I4 is equal to I1. I actually knew that when I started. Okay. All right. So if we do the following, first of all, I'll add VS both sides over here. So I've got R2, I2 equals VS. Then I added the second and third equations together, which canceled out the R2, I2, and left me with R3, I3 minus VS equals 0, which I took the liberty to write R3, I3 equals VS. Okay, is that all clear? Very straightforward. And then I can solve this for I3, I can solve this for I2, and then I can solve this for I1, right? So right, a solution like this, and then I4 equals I1. In parentheses there, this really didn't need I4 to start with, so I'm not going to go back here to delivery, make this into an I1. Okay. Well, there's my solution. I now know what the three currents are. And that's going to be consistent with what you get if you use the rule for parallel resistances. The total resistance there is R1, R2 over R1 plus R2. And you divide VS by that resistance. And you get the current. Somehow that that is bothering me just a little bit. Yeah, there's something, I've done something really kind of dumb here. I'm just trying to get my handle on what it is. Um, Just, do, do help the rules. I was really, I was thinking about that. I was just thinking it all. Okay, so there we have. The way it was before, the total resistance of this parallel combination would have been greater than the resistance of either resistor by itself, which is ridiculous. And I just did a really on everything else. So anyhow, there we have. You had your hand up and never goes at it. Okay, well, somebody was saying, there's an R3 up there. No, that's an R3. There's an R3 there. Oh, yeah, I had an R3 right there, didn't I? Again. Well, it lapsed into a bit of boneheadedness between here and here, but there it is. Okay, again, very easy equation. At least one person solved this using an automated matrix, which is very similar to the solution you get by elimination. And that's fine. That's actually more efficient. Okay, now if you're working on it, go ahead. I'm just gonna get this up. Do the same thing you're doing. So we've got this circuit. This little jump indicates that this wire is not connected to this wire. There's no node here. So there are 4 nodes. I call them A, B, C, and D, just so we can keep track. We'll keep this. And we've got 5 resistors. 1, 2, 3, 4, 5. Labeled R1 through R5. We want to find all the currents. So let's say I just start here. Pull this current. I1. Pull this current. I2. Pull this one. I3. And I don't care what direction I put this in. Here's I4. Here's I5. And so, yeah. This is I2. I1, I2, I3 in this one, I4 in this one. 1, 2, 3, 4, 5, and I have 3 units. Be 5, 6. Okay. Now what do I do? I'm going to pick on the nodes. And my nodes tell me that node A has negative I1 minus I2 minus I6 equals 0. Okay. Node B tells us that I2 is coming into node B, so that's positive. But I3 and I4 are going out, so minus I3 minus I4. And that's going to be 0. Node C, I have I1 and I4 coming in, I5 coming up. So I1 goes into node C. I4 goes out of node C and I5 goes out of C. Node D, I5 and I6 coming in. And then I've got I3 coming. Now, at this stage, I can eliminate some of these i's. Okay, I've got 4 equations. Now I've got 6 i's, so I'm not going to be able to solve for all of them. I should be able to eliminate some of them if I choose to do so. Okay. I need 2 more equations. I've got 6 unknowns. So I've got to choose 2 loops. Okay. Now everybody, I choose different loops. Um, but it's possible to choose 2 loops without the source voltage. I don't think that's necessarily a great idea. So anyway, I'm gonna choose one loop that contains the source voltage. Um, and I'll have loop A, B, D going in that direction. I'm going to have voltage drops I2, R3, and I3, R4. And then B1. If my voltage will drop across B1 if I follow the loop in this direction. And then, like any other loop, I'm going to do B, C, D. And I'm going to get I4, R4. I5, R1 minus I3, R4. Which is 0. Here. Now, here I've erased my B minus B1. And actually, I'm going to write this as equals negative B1 or negative. Okay, I'll call this B1. I'm going to call this BS. Okay, if I write the loop, I get a plus BS. That's a non-homogeneous term and a bunch of other equations, all of which are homogeneous. So I choose to go ahead and write it as I would if I was going to do an augmented matrix with a non-homogeneous system. Okay. Now I'm not going to work through all this, just I would just write all this as an augmented matrix, put it in the most reasonable form and reduce it. Although I might play around with eliminating some variables. For example, pick an I6, I say I6 is negative I3 plus I5, and I can replace I6 up here, then I have 3 equations, okay? And Similarly, I could say, well, I don't have it anywhere else. Not really a whole lot else I could do there. You get the idea. And you've solved a lot of simultaneous equations in your linear algebra course. So you're not gonna have any trouble as long as you write out the loops correctly and write it down carefully. Okay, we're just gonna kind of quickly talk a little bit about RC circuits. So they're fairly simple since you have the different equations background and everything, but let's just look at this. Okay, so you have a source, you have a capacitor, you have a resistor and series. Simple thing. When the charge on the capacitor is capital Q, from the board there, but capital Q will come. What's the potential difference across all? And then what therefore is the current. Now there is only one current in the circuit because any charge you deposit on one plate of the capacitor was pulled off of the other plate. Okay, so you do have accumulating charge in the capacitor, but you still have the same current throughout the circuit. Okay. So I think we got a good answer. Let's see. Charging capacitor is C. Okay, well, we reason this out. Capacitance is charge over voltage. Because a capacitor, a big capacitor is designed to hold a lot of charge for little voltage. Think back what dielectrics do. Think back to what having the plates closer together, further apart do. You really need to have all that together. Okay. So capacitance is charge over voltage. So voltage equals over capacitance. So V capacitor equals Q over C. Okay, so what's the current? And in terms of what we've just done, loops and so forth, you think of this as a single loop, just go ahead and put a current in here. Choose a direction. Okay, and now you write your voltage drops. Okay. Loop equation is if the loop, we usually make the loops go counterclockwise, but not necessarily. Because I can make another loop clockwise. So if our loop is clockwise, then we have a negative voltage drop here as voltage goes up. So we have negative DS plus IR now let's say plus Q over C. I didn't say which plate of this capacitor is positive and which one is negative, did I? Okay, so I'm going to say the voltage drop is Q over C. Then we're going to say that, okay, in that case, this is plus, this is the negative side of the capacitor, which is counter to what would the source would actually do. The source would actually, well, it is. Source would tend to push positive charge on here, although if you have more voltage across the capacitor than the source, the capacitor is going to push current back around this way, right? So the way I've got it, the source and the capacitor are opposed, but that's all right. I'll just specify that. So that's 0. Okay. Well, key here is the current's the rate of change of charge in the capacitor is what's the current is. Current's pulling charge off of one plate and putting it on the other, right? Now, is that a positive dq dt or a negative dq dt? Because if this is a positive, then if your current's in this direction, that's kind of not what the capacitor is doing. So let's just say, oh, guys, negative dq dt. Don't worry too much about that. At this point, so now you have negative ds plus r dq dt. I'll move this major minus plus q over c equals 0. That's not the best way to write the expression. But how are you going to solve that equation? Okay, I'm not sure how much of this I actually recorded. We put a source voltage resistance and capacitor in series around the loop. And we assume capacitor has positive charge here, negative charge here. And we don't really actually make that assumption right now, just have a little more detail to visualize and do that. And we want to find the current through the resistor when the charge of the capacitor is Q. Well, first we had to review too much about nature of capacitance. You know, it's a big capacitor. It's one that holds a lot of charge and voltage. So capacitance is charge divided by voltage. And more than that, you got, what happens with the plates of capacitor close over, perhaps you insert a dielectric. All that stuff on, a couple of chapters ago. People didn't seem to be highly aware of it. Now we just got off the woods spring rights. But you really need to be on. Okay. So if you got that, well then what therefore is occurring? Okay. First of all, capacitance is charge over voltage. So voltage is charge over capacitance. Voltage is Q over C. So now we know voltage across the capacitor. What's the current? Well, we know the resistance. We know the charge and the capacitance. We know the source voltage. So our loop equation gives us everything except the current. So we can easily solve this with the current. Now, I went a little further. I said that your currents, the way I've got this set up, it's negative dq over dt. Now, let me set it up a little more carefully. Usually just going to be plain old dq dt. And you get the differential equation. Okay. Should be a familiar type of differential equation. How you did differential equations like this when you looked at mechanical systems with right resistance and stuff like that. And there we have a very simple linear differential equation. It's non-homogeneous linear. So I asked to review non-homogeneous linear differential equations. That's only been a little over 6 months, not even 6 months since you have that course. So it should come back to you quickly, and it's going to cut through a lot of stuff to do that. Make all this much simpler. Excuse me. I don't think I'm sick anymore, but allergies. I got over the whatever that was I had. Just the top for allergies to make me seem like I'm still sick. I feel okay. Didn't feel okay then. Okay, anyhow, the this, so we get this. Now, just quick solution to the almost simple as possible differential equation. At x prime equals negative kx, our solution is x equals c equals negative kt. You get dx dt equals negative kx. You separate the solutions, you get dx over x equals negative kt. You get x then equals, well, natural log of x equals negative kt plus the constant, so that x equals e to the negative kt plus the constant. E to the constant gives you constant up front, and you get e to the negative kt, and that's something you just can't go through lifetime. Okay. This equation is exactly the same type if we remove the source. We have r dq dt plus q over c equals 0. Change that to q prime equals negative q over rc, which is exactly the same as this one, except it's q instead of x, and it's negative, well, it's 1 over rc instead of k. So here's our solution and our interpretation of our integration constant. The result of our integration constant is that's the initial charge of t equals 0. Because if t equals 0, we get q equals q naught. 0 is 1, q equals q naught, all that stuff. You want to get that down, and later on you're going to want to go back and review how you solve mechanical systems and discussions with your instructor. I think you did mechanical systems and didn't do circuits. Okay, there's a one-to-one analogy between mechanical systems and circuit resistances and drag forces and all that stuff. Absences. Well, anyhow, there's a very simple analogy, and so you got to review that at some point also. But for right now, make sure you understand solutions of linear non-homogeneous, linear homogeneous and linear non-homogeneous equations. And I mentioned I can ask you to do that only because everybody in the class has had differential equations. It's not something that's a prerequisite for the course. I can probably explain it in pretty simple terms. Without an assumption of differential equations that use your differential equations. It's going to be in your curriculum as you move on to Virginia Tech or other schools.